All right, let's get started. So why would you write a programming language? There might be good reasons for it. You might want to have some sort of domain-specific language that you need for some problem you're solving. You might want to find out what goes on under the hood in your favorite programming language. But the real reason for doing it is because it's basically the coolest thing you can do. So I have ambitions to write a proper language that solves all the problems we have with languages. So I decided to do the opposite of that and write a tiny little language that doesn't solve any problems, but helps me understand what a programming language is. If anything, it makes more problems than it solves. Okay, so in this talk, we're going to quickly go through what a programming language is. I'm going to introduce you to a little language that I wrote called CEL, which stands for Cell Elementary Learning Language. Then I'm going to talk about the 3 stages that it uses to do its work: lexing, parsing, and evaluating. So first of all, what is a programming language? Well, a programming language is something which takes in, at least according to me, takes in a text file or some other input, does something magical, and then produces either behavior or an executable that can be used to produce behavior. And for the purposes of this talk, we're only going to think about producing behavior directly. So this is an interpreter that I've written. There is actually, I did try and write a sort of a compiler. It was so bad that I didn't want to talk about it. Okay, so how do you do that? Well, what you do is you take in some text and you lex it. So the input to the lexer is some characters, and the output is some things called tokens, which we'll look at. Then you feed those tokens into something called a parser, which makes a tree structure out of them. And then you feed the tree structure into an evaluator, and the evaluator produces a value. And we'll get into what those things mean. So let's start off by having a quick look at CEL. I think I'll do you a quick demo of it really working just to prove that it really does. The primary design goal of CEL was that it was a short enough code that I could write a magazine article that contained all of its code, or almost all of its code. So that's very different from the design goals of most programming languages. And there are some trade-offs involved, some of which we'll see. It's intended to be understandable, but the need to be short means that there are some places where it's a little bit harder to understand than if I'd made it a bit longer. So I apologize for that, but we couldn't cover it if it wasn't that short, right? So it's on GitHub, but if you send pull requests that make it into a proper language, they're probably not going to get merged. Okay, so this is what the code looks like, and I'll do you a little demo. So I'm just going to run the interactive CEL interpreter just to prove that it really exists. So I can put a value into a name, like that. And I can define a function, like this. Oops. Like that. And then I can call a function like that. So the way you define a function might look a bit different from other things you've seen. Conceptually, it's the same. We'll talk about why I did it like that. Okay, so here's the same stuff, basically. Slightly different functions. So all functions are anonymous when you give them a name by using an assignment to a name. That hopefully will become clearer. So CEL consists of only 4 types of thing. Assignments, which put a value into a name. Operations, which combine 2 values together. Function calls, and function definitions. That's all there is. You can't reassign a name once you've got one, but there is a magic keyword, magic function, sorry, not keyword, magic function, which will modify the value of a name, value stored in a name. So from that point of view, it's a bit like Lisp, if that means anything to you. But there is something cool about Cell, something that I like, which is that things like if, which in other languages are a sort of special piece of syntax that is parsed in a special way. In Cell, if is just a function, which coincidentally makes the parser really small, but also is really cool. So this is what if looks like. So the downside is it looks horrible, but the upside is there's not much parsing. So there are other upsides, I think, as well. So if is a function that takes in 3 arguments. It takes in something which is going to be either true or false, and then it takes in references to 2 functions. And it will call the first one if the first argument is true, and the second one if the first argument is false. And now you can see why the brevity of the function definition syntax is important, because where in some other language you would pass in, you would be writing a code block. In Cell, you're defining an anonymous function. So that better look like a code block, otherwise you're going to hate it. I mean, you're going to hate it anyway, but we'll get on to it. Okay, other things about Cell. This bit of code is really just to tell you that scoping in Cell is sane and not insane like in some other languages, JavaScript. So when you put a value into a name inside a function definition, that doesn't change its value when you're outside of that function definition. Actually, if you put it like that, that's true of JavaScript as well. So this program prints hello world. Does that make sense? Can you now read Cell code? Because that's all there is. One other thing to say about scope, which is that obviously, because it's a grown-up language, in Cell you can return a function from a function and then call it later. And this is what we're doing here. So we have this function called outerFun. Inside there, we define something called innerFun, and then we return it. So the last line of a function is its return value. Probably should have said that. We return innerFun from outerFun, and then in the code at the bottom, we put the answer inside something called thing. So now that innerFun is in thing, and then we can call that by using bracket bracket. And because innerFun brings with it the context that's around it when it was defined, that works. And the output of this program is 12, because innerFun can see the value of x that was defined near its point of definition when it gets called later, because it has lexical scoping and closures, or because it's the only way it could work. Okay, so back to a programming language. We've got these different stages. We'll start by looking at the lexer. So the lexer takes in some text, produces some tokens. So if we look at a little bit of Cell code at the top, that code consists of a number of tokens of different types. Cell is written in Python. So what the lexer produces is a stream of Python tuples, which are the Lexing tokens. So what Lexing does is breaks up your code into, not into anything that has any meaning or structure, but just into the individual words that you've said to the computer, if that makes sense. So the word foo is of type symbol, and its value is foo. And then the word bar in quotes is of type string, and its value is bar. And the way we handle in Cell different token types that have very specific meanings to the parser is each of those special tokens has its own type. So in each of the tuples that you can see at the bottom, the type is the first value in the tuple. And then if there's any needed contents, that's in the second value. So the type of an equals token is just equals, because the parser is going to deal with it separately. I could equally have written the word equals or something else, but it makes it easier if it's just what it is. Also, slightly less code. Yeah, so in general, the job of the lexer is just to break stuff up into the bits that the parser is going to work with. When I first wrote a language, I was really tempted to combine lexing with parsing. I didn't know these words, and I just sort of wrote what I felt was right. And it quickly got really tangled up between those two jobs of just understanding the little chunks that you're working with versus the structure. On the other hand, the really cool kids who write Haskell with parser generators, they combine lexing and parsing because they're clever enough to do it. Just another example. There's tokens of type number, and there's tokens of type operator, and there's a few different operators. So in Cell, this is the complete list of all tokens that Cell's lexer understands. The examples aren't complete. There's a complete list of the types that you can see. So there's only one type called number, which is integers or floating point numbers. There are strings. You can have either type of quote. Yes?
Minus 42, is it an operator and a number, or is it the number itself?
I don't think you can have negative numbers. I think you have to write 0 minus 42. But that's the least of your problems when you're writing. I'm not sure. But when we get to the code, we'll be going through the code. We'll have a look at it. But I think you're just not allowed negative numbers. Strings can use either type of quote, though. So what are you complaining about? But there's no escaping. Symbols start with a letter or an underscore. There are 4 operators, and there's some other punctuation which is dealt with individually. So the rest of this talk will just be you reading the slide. No, don't read it. Don't read it. That's the whole code of the lexer. Okay, 40 lines. I was really pleased with that. I couldn't get it down anymore. The rest of this talk is us going through the code of Cell, but hopefully with readable text and more explanation. So the lexer is a function called lex. It takes in a stream of characters, which is pretty similar to a standard Python iterator that you can iterate through. But I need to be able to peek ahead one character in the stream, so I've made a little class that lets me do that. So chars, this argument to the lex function, is just something you can iterate through, but you can look ahead one without consuming it. So what the lexer does is loops through the characters that have been passed into it, and every time it has a token that it knows what to do with, it yields it. So if you're not familiar with the Python yield keyword, it's basically like returning multiple values. It makes an iterator. So when you say yield, you're just saying, here's the next value for your iterator. So if you don't know the yield keyword, don't worry about it. It's just like returning, just kind of like returning a value. What it means is that the return value of lex is an iterator of tokens. So the lexer is just a big switch statement, but you can't have switch statements in Python. Of course, in Cell, you could just write one as a function. And if you wanted one, you could just write one. But you can't do things like that in Python because it's not as flexible. So we have a character, which is the next character in our stream of characters that are coming in. At this point, we know we're at the beginning of a token, because if we were in the middle of a token, we wouldn't be in this bit of code. We'll see where we would be. So if we're expecting a token, but we get a piece of white space, i.e. a space or a new line, we do nothing. We don't yield anything. We just pass.
Sorry.
Yes.
Do you stand on tabs versus spaces?
Explicitly in the source code of Cell, a tab is an error. for the purposes of this talk, I've skipped over that so that no one gets too upset. But you can probably see it, actually, in the... Just here. We just throw. If you give us a tab, we throw. And then you'll learn not to do it. Okay, so the next type of token we might encounter is an operation. So if the character that we find is a plus or a minus or an asterisk or a forward slash, we immediately yield, slightly missing me. We immediately yield a token. So all of the operations in cell are one character long. And if we find any of those characters, we immediately know we found an operation token. So that wouldn't be the case in all languages, obviously. Most languages at least have an equals equals or something that you need to spend a bit more time lexing before you know you've got one. But cell's better than that. So you can see how you might, well, in a minute we'll see how you might generalize this to other things. But as soon as we found a plus or a minus at the beginning of something, we yield an operation. So this is the answer to your question. You're not allowed. We know this isn't a number. When you see a minus, we know it's a minus operation. Yeah, well, it's redundant anyway because you can do 0 minus. So that's how you get operations. Then the next case that we handle is just all the special cases of one character tokens that are just their own type. So we yield a Python tuple which has a type of the character we found and no value because you know enough already. So next we get to the more interesting things like a string. So if we find a single quote or a double quote, we know we're going to be lexing a string. So we call, again, we yield a token of type string, but this string is going to consist of multiple characters. So what we're doing here is kind of hiding behind the fact that actually inside the scan string function, we're going to go through the rest of the characters of this thing. So it kind of makes the outer switch look nicer than it really is, because really we're passing this mutable chars object into the scan string function and mutating it, which I really don't like. But it would be so many more lines of code to do something else. Honest. So, as far as I can see anyway. So, scan string takes in the this argument dilim, which is by which I mean whether you opened with a double quote or a single quote. So that's just the thing that tells you I've got to the end of the string. And it takes in this chars thing that you're going to iterate through. So this is what I mean. We're passing in the stream of characters, and we're taking some more out of it before we go back and yield. So this function is reasonably straightforward. We just go through all the characters until we find the character that tells us we've finished lexing a string. If that move next method returns none, that means we've hit the end of the stream of characters, which isn't allowed because we're in the middle of a string. So we'll throw at that point an extremely unhelpful error message. You'll never be able to figure out what's wrong in your program. Otherwise, we just collect the characters of that string until we get to the end, and then return the string. Yeah.
Strings are implicitly multi-line.
Yes, yeah. Anything you find before the end of the string, so including new line characters and tabs, which I'm unhappy about. I think what I'll say is that violates the language standard, but it's undefined behavior. So. Or possibly, maybe you need tabs in a string. I don't know. But what for? Notice that at the end of the string, you need to move on one more character to get past the quote. So this is the most complicated thing in the lexer. You've got this already. So. Next, we're going to cover the case of finding a number. I carefully tuned the width of these slides so they exactly fit on every device I tried. So if your token starts with a dot or any digit, we know it's a number. And the way we deal with that is similarly, we yield a token and call a function to get the rest of the stuff we're going to yield. And we already know the type, and we're going to find the value. And we call this function scan. And what scan takes in is the first character, because it's part of the number, the characters that it's going to iterate through, and then a regular expression telling it what other characters are allowed in that number. So if you're not familiar with the Python regular expression stuff, we're using it in a really dumb way here. We're just saying if there's a character that is a dot or 0 to 9. I could equally have written just in a string that has those things in it. It's not helpful. Okay, so the scan function is probably even simpler than the scan string function. We've already got the first character in this case. When we were scanning the string, we had a quote symbol, so we didn't need that to be in the value. But here we've got one of the characters of the number. So we put that into our ret value, and then we just loop through all the characters until we get to something that's not allowed, and then we stop. And this is an example of where we need to peek ahead in the stream of characters so that we don't consume something that might be needed by some other part of the lexer. So we take hold of this next thing, which is just a peek into what's coming in the stream. So just loop through these allowed characters in the number token. When we get something that isn't allowed, we must have finished our number, so we return it. And if you've been watching, you'll notice that not just valid numbers come out as number tokens, because you can have any number of dots in your number, and at some point later in the implementation, really far too late, we'll notice that and tell you that something went wrong in a really unhelpful way. So almost the last bit of the lexer is dealing with symbols, which are basically function names, variable names. So symbols can start with an underscore or any letter, but they can contain underscores, letters, and numbers. So hence why the scan function took in the kind of acceptable characters regular expression. So as soon as we find an underscore or a letter, we know that this is a symbol, so we can yield it, but then we go and find the rest of the characters. And we actually call the same function that we just looked at that dealt with numbers, but this time the list of acceptable characters is different. So again, it just goes on until it gets to something that's not allowed in a symbol, and it's finished. So this might possibly give you a bit of an insight into why in most of the programming languages we use, names of things can't start with numbers, because if you let them, then things just get awkward in terms of how you lex, because when you hit a number, it might be the start of a symbol, or it might be the start of a number. You could probably find a way of making that unambiguous, but most people haven't seen the need, I guess. And hopefully you can see how this generalizes to operations and things like that that have built out characters. So something that we have done that's made our lives easier here is we can always identify what type of token we're dealing with by the first character in that token. So that won't always be the case in all languages, but it just makes the lexer harder. But not really conceptually harder, just less fun to talk about in a talk. So yeah, if you hit a tab, or indeed any other unacceptable non-ASCII character we throw, that's obviously rubbish. And just to prove there are tests for this as well, here's one of my tests. So if we lex this string print hello world, and then which lex returns an iterator, so then we can make it into a list and compare it with this list of tuples, you can see it really does do what I said it did. Just to give you a little bit of a feel of how horrible it is to really code in Cell, I started writing a Cell compiler in Cell because That's what programming languages are for, writing programming languages. And it works, you know, all the code examples that I'm showing you work, but if you do something wrong, it just says you did something wrong, essentially. You know, it really doesn't try hard to tell you where, which is, it turns out just knowing where is basically all you need. Okay, so that was the lexer. So now let's look at the parser. So now we've broken up, we've just sort of chopped up the characters that were coming in into tokens. We know what type of token it is and what's in it, if that was relevant. And now we're going to make a tree structure out of it. We're not going to understand the code you've written, but we're going to recognize its structure, I guess is the way to put it. So here's an example of how I think about parsing. This isn't real, well, the top bit's real cell code, but the bottom bit's just a sort of a diagram. It's just that I do my diagrams in text. So an assignment statement turns into a tree structure. So this x equals something is an assignment, and then what the value that's getting in is itself another tree structure. So it could just be x equals 3, and then it's a small tree. But because it's x equals 3 plus 4, there's another layer of tree, which is the 3 plus 4 bit, which is the right-hand side of the assignment. So I've represented this by a sort of tree-like thing. So an abstract syntax tree for assignment consists of a symbol and the thing you're putting in that symbol. So the symbol is x, and the value is this next tree. That next tree is of type operation, and an operation has a type and arguments, and those arguments themselves could be smaller trees that go down, right? So this tree structure that we're making, the nodes, the parts of it are generally called abstract syntax tree nodes, but let's just call them tree structures. Here's another example. Calling a function gets parsed into a tree structure of type function call. The function that's being called is one piece of information you need, and then the arguments that are being passed in is the other piece of information, and that will be a list. And then each argument will itself be another tree structure with stuff in it. So in this case, there's one argument, and the value of that argument is a tree structure, which is an operation. With me so far? Feel free to ask questions at any point, by the way, if that wasn't clear, including now. Okay, so the actual Python is has a similar structure. So again, we're just using Python tuples. If I was doing this, if I had as many lines of code to work with as I wanted, I would have written these class things to represent data structures. But I don't have time for that. So these are just tuples as well. So the lexer tokens were just tuples that were always had size 2. These syntax tree nodes are tuples of varying length depending on their type. So they really would benefit from being classes. Yeah. So this one, for example, is of type call, and a call a call has 3 elements in its tuple: the type, and then the thing that's getting called, and then the arguments, and the arguments are a list. And the list is a list of other syntax tree nodes. For example, one that has a type operation, and then that has 3 more things in it. It has the type of operation and then the 2 things that are being operated on. Still with me?
Can you directly call a function definition?
Yes. Yeah, the question is, can you directly call a function definition? The answer is yes. So to translate that into this, the thing which says symbol print there doesn't have to be a symbol. That's why it doesn't just say print. It could, in fact, be some other tree of stuff that defines a function or calls a function which returns a function. Something. Okay, so this is the parser. There's 81 lines, so it doesn't look as impressive. So 40 lines you can pretty much read. 81 lines you can't, but that's it. That's all there is, and we're going to talk about almost all of it. So again, there's a function called parse, which takes in some tokens, and again, tokens is it's just something I can iterate through that I can also peek into. But in the definition of the parser, I've used one of these newfangled class things. I've made a class called parser. And what parser takes in is the tokens that you're going to be going through, and then the type of token that tells you you've finished parsing this particular thing. So you'll have noticed in the code examples, all the kind of complete statements in cell have a semicolon at the end, which is kind of annoying, but it's much easier to parse. So again, you're noticing a pattern. So what we do is we make a parser, and then we ask that parser for the next expression a lot of times. If it gives us back none, then that means I have nothing to give you. If it gives us back something, then we effectively just return it, we yield it. So again, this parse function returns an iterator, and we just keep moving through tokens and ask the parser, give me a syntax tree. If the parser's not ready, it will return none. This is how we construct the parser, so there's nothing clever here. It just keeps hold of it. This is just really for completeness, right? So you've seen almost all the lines of code. And then the next expert is where we start getting into the logic. This is like a bit of preamble, and then we'll get onto another big if-elif statement in a minute, which looks surprisingly like the lexer. So in a few places in the code, you'll see this fail if at end function method. All that does is, if we've got to the end of our stream of tokens, it throws an exception. So you can effectively ignore that. It's just saying, I was expecting to find a semicolon, hence why we pass in the semicolon. But I didn't because I got to the end of the stream of tokens. So it's a parser error. So assuming we're not at the end of the stream of tokens, we get the next token, and we unpack that token into a type and a value, because lexer tokens are just a type and a value. And then if the type tells us that we're going to stop parsing, then we return what we've already got. So I haven't talked yet about what we've already got. So when we call next expr, we pass in the bit of the expression we've already done some parsing on. So at the beginning here, when we call next expr, we pass in none because we haven't done anything yet. But if we get to the end of our parsing, then we've finished. So whatever we've already parsed is our result. So it was passed in as prev, and we return it. So I think maybe someone should send me a pull request to make this bit simpler. And anyway, so passing over that special case, we just move on to the next token coming from the lexer. And then we have a great big switch statement, which helps us identify what tree structure we should make based on the tokens that are coming in. But in this case, unlike the lexer, in the parser, we don't know immediately what type of tree structure we're going to build based on just one token coming from the lexer. So we have to be a little bit clever in two ways. First of all, let's go through it. So, so the first case to handle is if we haven't parsed anything yet, so prev is none, but then we've now hit a token of a certain type, number, string, or symbol, then in some sense we've finished. We've got a potentially complete bit of parsing done. But there might be some more stuff that follows on after that. So we don't just return an answer. What we do is, what we know is that we've now got enough that the next thing we find is going to help us identify what type of tree we should build. So we've got one thing we know. In the case of cell, we know that when we hit the second token, we're going to know what to do with this, because it's going to be a plus or an open bracket or something that identifies the type of structure we want. So all we do is wrap that up, wrap that type and value back together and pass them to nextExpr as prev. So now we've done a bit of parsing. We've found this string number or symbol, and we're recursively calling nextExpr, passing that as, this is the thing we've already parsed, this number now, or this symbol or this string. Now you may want to do something else with it, or you may find a semicolon and just return it straight back. So again, if there was a class called syntax tree node, then we would be constructing one here, but instead we're making a tuple of type and value, which happens to be identical to the lexer token, but in this case it's not a lexer token, it's an abstract syntax tree node, okay? So bear that in mind at all times. So the next thing that we might hit is we're running through our stream of tokens and we hit a operation, like a plus or a minus. So in this case, if you haven't got anything in prev, something's gone wrong. You shouldn't hit a plus if you haven't already hit a number or something else. But we don't check for that. We haven't got time. So we just get on with it. We return, we don't quite return. We know now that we've got an operation. Or we know that we've got a tree node of type operation, not to be confused with a lexer token of type operation. They're completely different. But we might not have finished parsing, so we don't just return an operation. We return the result of calling nextExpr. So, because a lot of these expressions can have more stuff that comes after them. So, for example, if you call a function, that might return a function. You may then want to call its return value. So you can have bracket, 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 and call lots of functions one after another. Yeah, sorry, yeah.
Does that mean 1 plus 2 times 3 is equal to 9 instead of 7?
Yes. Yes, it does. It's the first language to have a really easy to understand operator precedence. I actually really hate operator precedence, just as a side note. Just because mathematicians know what order to multiply things, life is so much easier for mathematicians. We shouldn't complicate our lives by trying to do what mathematicians do. They like different things. Because the point about maths is once you've thought about something once, you don't have to think about it again, but that's just not true for us. Okay, so we're making, so that was all just preamble to say, we're going to make an operation, and then we're going to pass it back into another recursive call to nextExpr, because there might be more coming later. But then operation needs, it needs to know the type of operation this is, like plus or minus or times or divide, but it also needs the two things that are being operated on. So we know the first thing that's being operated on because we've already parsed that came already, but we need the next thing that we're going to operate on. So hence why we have this variable called next. And what we do is we recursively call nextExpr, passing in none to say, go and get me the next, the other side of the operation. Once we've done that, we've got an operation, and we can recursively call ourselves with something in the prev argument to say, I've finished this expression, but there might be something after it. So the reason we pass in none to nextExpr is because from the point of view of that bit of parsing that we're doing, there's nothing already existing. We just want something that's kind of standalone on the right-hand side of that operation. So go get me that, if it's 3 plus 4, go and get me that 4, bring it back, and I'll combine it into an operation as the right-hand side, or the next. In that operation. With me so far? You can just nod if you'd rather just get to the end. Okay, so the next type of thing that we're going to deal with is if we have a token which is an open bracket, that means this is a function call. So bear in mind that we're uncovering another little feature of Cell, which is that there's no grouping of things using brackets. If you really want to group some things using brackets, for example, to help with the operator precedence problem we talked about, you'll need to make a function that does nothing, right? And then you can call it. It'll be fine. I might put that in the standard library. So you can't group things by putting brackets around them. But yeah, it really makes life a lot easier. I'd have to deal with other cases. In fact, it'd probably be quite easy because, yeah, anyway, okay. So, so now we know we've got a function call. So prev contains the function that we're calling, which might be a symbol or it might be function definition or something. So what we need to do is go and get all the arguments to the function, and then once we've gone and got all the arguments, we can return a syntax tree of type call. But as I was saying before, a function call might be followed by, it might get called again. So we still need to recursively call next expr once we've completed this function call. So the hard bit is this multi-exprs method, which basically has to go through and parse each argument one by one and then return them all. And then we use that as the args of the third element in the tuple for our function call syntax tree. So how do we go and find all the arguments? Well, they're separated by commas, and you know you've finished when you get to a closing bracket. So multi-exprs takes in a separator and an end token. It checks to see we haven't finished our string of tokens because that would be an error because we need a round bracket. And then it loops through, and if we've hit the end, the closing bracket in this case, then we stop, just move past the closing bracket and then return. And then the interesting stuff happens in the else. In the else, we make a new parser because what stops us parsing is different from what it was last time. So now, in this case, what stops us parsing is either a comma or a closing bracket. So if you were watching very closely, where we were looking for that ending token, we weren't just looking for one thing. We'd actually passed in a string and that string is being interpreted as a list of things that make us stop. It's just that it happened to be only one thing when it was a semicolon. Now we're passing in a list of two things, which is either a comma or a closing bracket in this case. With me? Okay. That was all. It's not that important. So anyway, we make a parser and we tell it you can stop when you hit either a comma or a closing bracket. And then we loop through, and so we're reusing this parser several times to get hold of each argument one by one. So we ask the parser to give us the next expression. If we've got one, we put it into the value we're going to return. Now, and obviously sometimes the parser will return as null, which means I didn't find you anything, just keep going. And that's basically it. Move through tokens and fail if you got to the end. So we're just reusing that parser with a different end, and basically the rest of it is going to happen for us automatically. So we just look for things separated by brackets and stop when we get to the close bracket. Still with me? Questions? So let's just go back to where we were for a second. So that was, if we find an opening bracket, that means we're calling a function. All of that was just, here's how we find the arguments to that function. Once we've found them, we've finished parsing a function call with a thing that's getting called and arguments, and we pass that into next expr because there might be more to come. So the next type of thing that we need to parse is a function definition. So we've done a function call, that was the open round bracket. Now we're going to do a function definition. Function definitions unconventionally start with a curly bracket. But now that I've done it, I really think it's right. And it's kind of similar to, it's inspired by Ruby. It's not completely out of nowhere. Anyway, so we define a function. We know we're defining a function because we found a curly bracket. There should be nothing in prev, but we don't check that. This is kind of it's sort of a talk, sort of a code review. No, we don't check it because we don't have time. So in order to handle a function definition is a curly bracket and then optionally followed by colon, round bracket, list of argument names, close round bracket. Remember that bit? That's the bit I'm not showing you how we parse that because it's too easy. We only do the difficult bits. So parameters list goes and parses that if it's there, but it's too easy. So we're just going to go straight on to calling multi-explorers again, but this time, instead of looking, last time we were looking for commas and round brackets, now we're looking for things that are separated by semicolons and stop when they get to curly brackets. So, yeah, we're almost done with this, with the parser. Don't get too excited, we've still got the evaluator. So once we've found a curly bracket, we know that what we're making is a function definition. So the function definition consists of, is a tuple which just says the type, and then two more things, the list of parameter names, and the body of the function, which is just a list of expressions, the last of which is the return value. So again, because of the example that Charles mentioned, if you define a function and immediately call it, which JavaScript people like doing, this works because, the only reason this works is because we call nextExplore here instead of just returning it straight away. Okay, so one more thing to handle, an assignment statement. So if we find an equal sign, we know we're in an assignment statement. And here there's a bit of error checking. If the thing before the equal sign isn't a symbol, we throw and tell you in a useful way. Not that useful, because he still doesn't tell you where we are. So similar to what we saw before, we're in an assignment statement. We need to go and find the stuff that's on the right-hand side of the assignment statement. So we call nextExplore and pass in none because it's independent from the rest of it. Once we've got back the stuff that's on the right-hand side of the assignment statement, then we return a syntax tree of type assignment, which has two other parts to it, the thing before the equal sign and the thing after the equal sign. The thing before the equal sign has to be a symbol. The thing after could be any other syntax tree. And again, in theory, there could be some other bit of stuff after this assignment, although actually in the current implementation, there's nothing that would make sense to be there. But again, we call nextExplore just for consistency with the rest. Because in principle, an assignment could then end up, like everything in Cell, everything is an expression, not a statement, so an assignment returns the value that got assigned into the variable. And in theory, you might, if there was some way of making the parser do it, you might then be able to do something else with that value, but I don't think there is a way of. Probably shouldn't figure that out right now. So if it's not one of those things, then we didn't recognize what you gave us, and we throw. It's essentially parser error. So a lot of the times when you make a typo when you're programming, it says parser error. This is where it's got to in the parser, because it's as easy as this. So we're getting through it. We've done turning text into tokens by chopping it up. We've done taking those tokens and organizing them into a structure, which you could call understanding, but really nothing's been understood yet. It's just been recognized. Structure has been recognized. But we're getting on to the magic of understanding what you said to the computer. So we're going to do a quick recap. Lexing chops up the symbols and gives you these tokens, which are always length 2. Parsing recognizes tree structures and returns them as tuples within tuples within tuples. Cell looks like that. Functions are defined with a curly bracket and then a list of variable names, and a list of statements separated by semicolon. You call functions in the way that you like. And then an important recap for the next bit we're about to cover. This is the way scope works. So when I define this thing called inner fun, when I define the right-hand side that's getting assigned into inner fun, part of that function definition process has to be to get hold of the scope that we're in so that that value of x is available to me later when I ask for it. And that's why this prints out 12. It doesn't fail, yeah.
Why do you have the colon in your function definition?
I just liked it. I thought, well, yeah. So it's only there when you define when you provide, when there are some arguments. So functions that don't take any arguments don't have a colon. So I like the lack of ambiguity that it gives you, that you're not starting some expression that starts with a bracket. However, of course, in Cell, there are no expressions that start with brackets. So actually, it would be fine. But I don't know. It just need that tiny bit more syntax to be allowed to define a function. Otherwise, it's too easy. Designing this syntax, I had half a mind to trying to write a proper language which has some of the same ideas. So maybe that's my excuse. Just felt right. So we just talk about environments before we talk about evaluation. And you can think of an environment as the place where you are. So when you are in your house, you can see the things in your house. So if you're in a particular bit of source code in a particular function, you can see the stuff that's defined in there. So you might have a function called myFunction that you can see from where you are. But then your house is in a city, and you can see all the things in your city. So you might be using a library which has a JSON parser in it. And you can see that from where you are. And then the city is in a world, and you can see everything in the world. So the standard library functions are visible to you from wherever you are. So this is kind of like, it's like a parent-child hierarchy, where the place where you are can see the place that it's in, and that can see the place that it's in. So we define that in a really simple class called env. I have no excuse for why it's not called environment. An env has a get method. You ask it for a name. It looks inside its own list of things, and if it's not there, it checks whether it's got a parent, and if it has got a parent, it asks the parent for that thing. So that's how you get the lexical scoping, where you can talk about X when you're inside a function, and it means something different to someone who's not in the same environment as you. With me? Yeah.
So is environment the same as scope, or is scope specifically different to environment? Or have you just chosen to try and not use that overload term?
I think they're the same thing. Scope, I'm using scope to talk about the concept, and then environment to talk about this sort of implementation of the concept, maybe?
Scope is a lifetime environment.
Well, lexical scoping as a concept, is that to do with lifetime? I don't know.
Yeah, I mean, here they're coincident.
Right, that's why, yeah. Yeah, so because Cell is an interpreter and the interpreter environment lives inside the Python interpreter, lifetime is just handled. And set is as simple as you would hope it is. If you set a value in an environment, it gets set up in your local environment. It doesn't modify the parent, and that's why it's not JavaScript. So this is Cell's evaluator, and some of those lines are easier than the lines we've looked at already. Yeah. So eval_expr is the core of the evaluator. There's a couple of other functions that evaluate everything in the list and things that I'm not literally showing you, but I can show you that slide again later if you want to. But all the interesting stuff happens inside eval_expr. Eval_expr takes in an environment in which to do the evaluation. You can't evaluate things without an environment that you're in, because the same expression, the same syntax tree, will have a different value in a different environment. Or won't make any sense at all. Okay, so we're taking in syntax trees, so they always have a type, which is the first thing in the tuple. And some of them are simple. For example, a number. So if you have a syntax tree which represents a number, that's just got two things. It's got the type and the value. But the value is a string at this point. In the syntax tree, we didn't do anything with that number. We just collected up its characters. And this may still contain a lot of dots. Right? And this is where you'll find out, because there'll be when you run your code, there'll be an easy to understand number format exception. It also, coincidentally, Cell's definition of a number is exactly the same as Python's definition of a float, which works out nicely because this is only one line. But in principle, we could understand those multiple dots as meaning something or whatever. We could do anything we like. This is where we understand the meaning of your code, finally. Strings are really, really easy. Again, a syntax tree node of type string only has two elements in it. The first thing is the type, which is string, and the second thing is the contents of the string. So we can yield a value of type string. I should really say that. So what we're returning here is not a lexer token or a syntax tree node. It's a value of type number. And this is a value of type string, which looks exactly the same as both the abstract syntax tree and the lexer token, but they're completely different things. And again, Cell happens to agree with Python about the exact definition of a string, except for all the things that aren't allowed in the Cell string because it doesn't know so many ideas like escaping. Something else that we haven't covered at all, because it's part of the standard library, which we're not covering in this talk. It's extensive, as you can imagine, it's an extensive standard library. There is one special value defined in the standard library, which has a type of none, and you can refer to it in your code using the word none with a capital N. But it's just a value that's defined. It's nothing special, so we haven't had to cover it in this, except that the evaluator needs to know what to do with it. What it does with it is it finds a abstract syntax tree node of type none, and it returns a value of type none that happens to look the same. Then we get on to the interesting things. So if you find an abstract syntax tree node of type operation, in order to evaluate that and understand that, we have to actually do something. So now we get to things that do things. So here's the operation function. What the operation function does is it evaluates the two things that were given to it. So this is a tuple with a type and then the two things that are getting, the type and then the operation itself, which is plus or minus or something, and then two things which are the two things that are getting combined. So the first thing we need to do, because we're in this tree structure, is we need to go further into the tree and evaluate the things that are in the two sides of the tree. So we recursively call eval expr. Once we've got back the two answers, then we just do the right thing. We know how to perform the different operations. And again, as luck would have it, when you find a plus operation, that's identical to Python's plus on floats, so we just do it. But here again, this is where we're actually understanding what you wrote, and we could be using the Python big int implementation of a number and doing the relevant plus operation on that, and then we'd have a different idea of a number from Python.
Just looking at that, I can't see any reason why you couldn't add two strings. It would claim it was a number, but it looks like the Python code might actually still do something.
Yeah, probably. Yeah, I should think so.
It's a bit mixed that you'll get the problem
It's not a bad style.
Yeah. Yeah, so if you violate the language standards, anything could happen. So even possibly something logical. Yeah, I don't know. Was that your question as well? Yeah. Yeah, so, I mean, woe betide you if you try and add up something else that really doesn't make sense at all.
What happens when you call print 1 minus 2? Negative number?
Yeah, that's a good question. Should we try it? Oops, semicolon. It worked. Yeah, so it worked coincidentally because print uses Python's idea of print, so it's ended up with a number that Cell has no way of representing, or rather you have no way of telling Cell about, but Cell is perfectly happy to hold on to it for you. And when it prints it, Python will print it for you, so you're fine.
What happens if you print space times 3?
yeah, then that would be an error. Oh no, that'll probably be fine. That'll probably be fine. In fact, we don't even need the print for this, I think. Oops, there we go. Yeah, so yeah, it's a float. Yeah. So you've jumped directly there into Python. So you get all the benefits of Python's error messages. So yeah, so the big thing that's missing from Cell, apart from some of the things about the syntax are awkward, the big thing is the error handling, which is a really hard and interesting problem, but not as cool as this stuff. So. But yeah, so the point here is that it's a coincidence that plus happens to be implemented by plus in Python. We could have called it something else. We could have made the star operation be a plus in numbers. So this is, the reason why I'm emphasizing that is because if you're looking for where's the magic bit that actually does something, this is it. Okay, so if we found a symbol, so what the evaluator is doing is taking in a tree of structure and turning it into a single value. Each whole tree, evaluate all the leaves, pull it all together, end up with a value. So how to do that with a symbol is go and look it up in the environment. So we get its name, which is the second thing in its tuple, and we ask the environment for it. And if the environment, which goes and asks all of its parent environments, can't find it, that's an error, and we throw it. That was too quick. Is that all right? Yeah, that's because it's easy. Okay, so assignment, as in x equals 3 or something like that. What we need to happen here to evaluate this expression has a side effect of modifying the environment that we're in. Well, maybe calling it a side effect is wrong. From Cell's point of view, it's not a side effect. Anyway, this expression returns a value and also modifies the environment that you're in. So the value that it returns is just whatever was on the right-hand side of the assignment, and that's also the value that it puts into the name. Yeah, sorry, the right-hand side of the assignment, but that's also the value it puts into the name. So all we need to do is call eval_expr recursively, passing in the thing that's on the right-hand side of the assignment, which is just the last thing in the tuple of the assignment syntax tree that we were given, so expr brackets 2. So we call eval_expr, and that gives us back, that does its own bit of evaluation, finds the value that was on the right-hand side after the equals, and then we call env.set to put that value into that name in the environment, but we will also return val in case you want to do that. Because everything is an expression, everything has a value. Still with me?
So why did you put the extra code in to prevent overwriting?
Why did I put the extra code in to prevent overwriting? Because it violates the language standard too.
Many other things which violate the language standard go unpunished.
Yeah, but violating the language standard in a way that doesn't affect whether your code is better or worse is not explicitly checked for. Violating the language standard in a way that makes your code worse is checked for. The names should only have one value, except for when you use the special built-in set function and change their value.
Can you chain together assignments?
Can you what, sorry?
Can you chain together assignments? So could you do something like A equals B equals 2?
Yes. Yes, we try it. You should be able to. Semicolon. Oh, yeah. Yeah, it works. Yeah, that's good. That's good. That's good. The reference implementation fits with the standard. Yeah. Okay, so the other things we have to deal with are the hard things, right? So don't stop listening yet. So we have to deal with function calls and function definitions. And we're going to do them in the illogical order by doing function calls first. So function calls get their own function because they're complicated enough. In order to evaluate a function call, you just call the function, run the code of the function in an environment. So this is why the environment got passed in. So first thing we have to do is call eval_explore in order to get the thing that's getting called. So that could just be a symbol, in which case we need to go and look it up and find the function definition that it refers to, or it could be some sort of inline function definition that's getting immediately called. Either way, we need to evaluate it to find the thing we're calling. Then we need to evaluate all the arguments so that we can pass them in to call the function with them. And in most languages, you'll find that the standard defines that the arguments get evaluated before you call a function passing them in. And the reason is because there's approximately this code, right? It evaluates all the arguments and then it passes them to the function, apart from Haskell, which we won't talk about. Also, as you can see from the implementation, we guarantee the order in which we evaluate our arguments. But I don't know whether that's in the standard or not. But once we've got hold of a function, so that's nothing clever there, it goes through the arguments which are provided in the tuple of the syntax tree and just evaluates them. Once we've got hold of this thing called fun, which is a function, there are two possible things it might be. It might be a function definition that's defined in cell code, in which case the first thing in the tuple will be function. And we'll see in a minute how you make one of them, or how the evaluator makes one of them. Or it might be a built-in native function, so which in this implementation of cell will be a function written in Python. Unfortunately, you need a couple of them. You can't just write everything in cell. Sorry? Yeah. Yes, you need if. Yeah. Annoyingly, you need if. And you need set, which I haven't talked about.
Do you check for a function of the name state definition? If you have two functions with the same name, the second overrides the first?
If you were trying to assign them in the same environment, you'll hit that line of code that Charles was complaining about, and it'll throw if you try and redefine a name. If you redefine a name in a deeper in environment, then it'll happily that will be the name for that bit, and then when you come back out again, the other name will be back to being the name. So you can sort of override further in the scope. Not override. Definitely not overload. Mask, shadow, yeah. Okay, so if this is a function written in cell, then we check the number of arguments matches. So the function definition has its idea of the number of arguments, and then you've called it with a certain number of arguments, and they must be the same. So we check that by calling a very simple function called fairless wrong number of arguments. What that uses is explore brackets 1, which is the arguments that are being passed to the function. Then we get hold of the body of the function, which is a list of expressions. And we get hold of the environment that was stored with the function when it was defined. In a minute, we'll see where that happens. But fun_env is the environment that was stored with the function at the time it was defined, which is how that x that was 12 is still available, because the function definition holds on to that environment which was containing the definition. That is lexical scope, and that is how we as a programming community have agreed scope is going to work. So once we've done that, we make a new environment. The reason we make a new environment is because we need to put all the arguments that you've passed in this particular call of the function into an environment so they can be looked up by the expressions in the body. So we make a new environment, and we call set in that environment for all the arguments using the name that you provided in the definition and the value you've provided in the call. Once we've got an environment, we call eval list, which basically just evaluates everything in a list by calling again recursively into eval_explore. So now we've called a function. The other thing that might happen is that we're calling a function that is native, so it's written in Python. That Python function is still there in this function definition object we're dealing with. So fun brackets 1 is actually a Python function in this definition. We check the number of arguments again, and then we call the Python function directly right there, just like that. But we pass in an extra argument because we need to know what environment we're operating inside. So the Python function, for example, if, doesn't just take in the 3 arguments we've seen it takes in cell, it takes in this extra argument at the beginning, which is the environment in which it's operating. I really wish I could show you that. It's there somewhere. We can look at it afterwards if anyone's interested. And if we're trying to call something that's not a function or a native function, we throw. And we get on to the last and possibly hardest thing, which is how do I evaluate definition of a function? Actually, this is easier than what we've done, so okay, it's okay. We've gone past the worst. So we've hit a syntax tree of type function. And so that's a function definition. We need to return a value which is a defined function, a thing that you can call. So we return this tuple, which basically is just a collection of the stuff you've already got, which is the argument, names of the arguments, and the body, which are the expr1 and expr2. And then here we make a new environment based on the environment we're in at that moment, and that is how we carry this environment with us. The number of nods is going down. And if we didn't know how to evaluate this type of parse tree, which should never happen, we throw. And the end result of all of this code is that we end up with, for every expression that's written in cell, we end up with a value. So this tree has been reduced down to just one thing. Oh, and also there might have been some side effects, like if you called a native function called print, it might have had a side effect of doing something in the outside world. And that is really how you write a programming language. And the reason why it's only just over 200 lines of code is because it's actually really quite conceptually simple. I mean, I've missed out all the hard bits, as we've talked about, and I've missed out all the other hard bits, like optimization and code generation things. But a big reason why it's easier than you might have thought, if you did, is that we normally learn this stuff by writing it in machine code, and you know, there's some use in that, but we're actually combining 2 things together there. We're combining how to do kind of high-level concepts like calling a function or recursion or something like that, with the concepts of the programming language, which I hope I've demonstrated, make sense in a high-level language, where we can do things like recursion, which makes life so much easier that we can just call eval expr again, and we know that there's a stack or something, and it all works. That's that.